the implementation of the training algorithm. And so our code was, plain English, it was like this: read training data into NumPy array. Okay, so in the beginning, for example, it was of size 1028, correct? Then next thing we do is reshape it to to 1000, 784, 1. Okay. Also, we read expected outputs. Okay, and the way, one way to do that is, okay, see, okay, if you take a look at the, for example, the MNIST data. Okay, when they store the images that I will provide to you already have been converted to a bitmap. So there will be a BMP file. For example, if the BMP file says 234.bmp. So what does that mean? That means the digit is 2. Okay, and file number 34 or whatever, right? So the first character over here tells us what is the digit. So for example, if you have a file 705.bmp, what does it correspond to? Number 7, right? Okay, so in our case, the question is, as we read the expected output from what we want to do is, we want to create an array like 1000, 10, okay, such that in case of this file, 0, 0, 1, 2, 3, 4, 5, 6, 7 will be 1, 8, 9 will be 0. So we want this data to be stored if we read this particular file. Okay. So the way, I can show you the code in a second, is what I'm doing is once I go through a folder, I loop through it, I pick the first character out of here. Okay. And then once I initialize this array, this Y array, so Y equal to NP dot zeros and shape of 1000, 10. So this is how I created it, right? As I'm looping through the folder, picking up a file, I'll say Y, whatever I or J loop is, equal to whatever data I read, okay? And then what I do is, for the character, if it was 7, I'll convert to an integer, and that for that integer, okay, suppose that's called J, I'll set it to 1, because everything else by default is already zeros anyway. So just for that particular row, I set it to 1. So let me quickly show you that part, and I'll provide you that code so that at least reading the data is straightforward for you guys. for some, oh, there we go. So let's do this. Okay, so anyway, the reading data code. Okay, so this is where I'm looping through the folder, right? And if you take a look over here, y equal to int of file name of 0. So if it was 705, this will be 7, right? And train of y, I comma y equal to 1. So only in the beginning, once I created train of y, I initialized it to everything to zeros. Okay. The bitmap itself, all will be read into the regular train folder. So this is the expected output. So train of y is the expected output. So anyway, just for that part, we'll make it 1. So that was right. Okay. So now let me talk about 3 variations of the algorithm, training algorithm, and then I'll come back to this in a minute. So let me give you the idea first. Okay, so as far as the backpropagation algorithm is concerned, okay, there are 3 variations of it. One is called stochastic gradient descent. One is called batch gradient descent, or sometimes called min batch. And the third one is simply gradient descent. Actually, let me just call it mini batch so that there's no confusion. Okay, so what's the difference between the 3 algorithms? The difference is pretty straightforward. Okay, as I mentioned, we go into for I equal to 0 to number of epochs. For j equal to 0 to whatever the training data is. So training data size. Okay, for example, 1000 in our example, right? Okay, so then we do the forward pass. Okay, we compute deltas and delts, like del W1, del W2, and so on, right? W2. So basically, let me just put over here del W1, del W2, B1, del B1, del B2, right? And then what do we do?
Loss calculation.
Yeah, we also calculate the loss over here, so over here.
Then
Okay. So then we adjust the widths, right? So then W1 equal to W1 minus the learning rate times whatever del W1 is. Okay, and so on for W2, for B1 and B2. So this, for every sample, we are repeating this. So this is called stochastic gradient descent, with the difference being what we do is we, when we are done with one epoch, we shuffle the data. So basically, shuffle the data after each epoch, so that we are not picking the same sequence like training data 0, training data 1, training data 2, and 3 and 4. So first time we'll go in sequence, second times we'll reshuffle the data so that the order in which we compute these is different from the first epoch. And that's what means stochastic. Okay, keep changing the order every time as you go through the loop, right? Okay, that's one version of it. What's the mini-batch version of it? Or let me go to the regular gradient descent version of it. In the regular gradient descent version of it, we do not do the update after each training data. Okay, so this goes away. So in fact, as we compute these delta W1, we do a plus equal to. Or, because these are matrix operations, so basically delta W1 plus and so on. Delta W2 equal to delta W2 plus. So what does that mean? Before we start over here, set delta W1, delta W2, delta B1, delta B2 to all of them to zeros. Okay? Because remember, whatever the old value is, we are accumulating it. Okay? So let's say we have 1,000 training data. We went through 1,000 times. So how many times it got added? 1,000 times, right? Okay, now what we'll do is at the end of this loop, so after we are done with all the training data, then previously in the stochastic part, right here, we were doing the updates. Now we will go outside of this loop, and now we will do W1 equal to W1 minus the learning rate. Times, okay, I'm writing in plain English. Of course, you will do it properly using whatever the NumPy operation is. Okay, divided by 1,000 in this example. Or the length of, you can determine the size of the training data. So this is the training data dot length. Okay. Okay, and the reason we are doing it because we accumulated 1,000 times. So at the end, as we update, we have to same thing over here divided by 1,000, and same thing for B1, B2. So at the very end, after going through the entire training data, after accumulating all the gradients, then we update the weights. So think about it this way. What's the difference between stochastic part where right here after each one we were updating the weights?
It was initialized to random, right? In that case.
Right, but it has nothing to do. So in one case, every training data is causing a change in the weight. In the other case, at the very end of all looping through all the training data, so isn't this like average of all the gradients?
Yes.
Okay, so if we try to plot how the loss is behaving and compare them between stochastic and the gradient descent, what you will see is if the loss is high in the beginning, right? So this is our loss, and here's the epoch. Okay. So what you will see is in this particular, in the stochastic gradient descent, we will do something like this. And then probably become low if it was still programmed properly, right? Whereas so this is the behavior of the stochastic. Actually, let me do it a little bit. Let me redraw it a little bit better. So something like this. Okay. It may not go to 0, it may go still be some value there. So this is how the stochastic will behave. Okay. If we try to compare it with the regular gradient descent, then it will look something like this. Okay, so you'll see, because the changes are slow, right? After an entire 1,000, then we update the weight. So the loss will become very gradually down, but it will not fluctuate up and down so much because we are taking the average of all the data, right? So the mini batch is considered to be the best approach. So here, it's basically a trade-off between the two techniques. Okay, rather than accumulating all 1,000 gradients, okay, here what we'll do is we'll basically have a third loop for k equal to, for example, j plus 50. Okay, so we'll pick the kth sample. I shouldn't say k equal to j plus 50 for k equal to j2 j plus 50. So first time through the loop, we'll accumulate 50 of these. Okay, then after the 50 are done, then, sorry, this loop will now be after the k loop. So after this k loop, then we'll update the weights. And so then what will this be divided by?
50.
50. Okay. Anyway, rest of the code stays the same. After 50, we'll zero out. So this will basically now move over here. So we'll zero out after 50, and we'll keep going until we've gone through all the training data. And again, we'll shuffle so that it has a stochastic behavior as well. So anyway, this is considered typically the best approach. Okay, let me quickly show you the C# code that you will, so your next assignment, let me briefly tell you what your next assignment will be. So your assignment, and I will formally put it on the website, will be, you'll do a classification of MNIST data set using dense neural network, dense two-layer network. Okay, one of the things that I'd like you to do is, okay, so remember we have two layers, right? Our inputs will always be 784. Then our first layer, suppose we'll have 100 neurons. And then second layer, as we discussed, is dependent on the problem, so it will be 10 neurons. Okay. So what if we, instead of 100, we use, so anyway, you'll train the network, so you will, okay, so you will train it on 1,000 images, even though the MNIST data set gives you 60,000 images for training, because a lot of you will be doing on your laptops and it will take too long. So I'll cut it down the data set. So you'll train it on 1,000 images. Okay, however, you will test it on all images, all test images. And in the MNIST data set, there are 10,000 of these test images. And then you'll see which one produces the accurate answer. We have 10 outputs over here, correct? Okay, suppose you pick one of the test image after your network has been trained, and you feed in, let's say, a 7. So suppose it produces an output like 0.3, 0.6, 0.1, and so on. Everything else is, the highest number it produced was over here.
So I think it's a 1.
It failed.
So it thinks it's a 1. So that's a misclassification. Okay. For it to be accurate, the 8th output has to be
The highest.
the highest.
Closer to 1.
Yeah.
It doesn't have to be 1, but it has to be the highest of all the numbers.
It will be never 1.
Okay. So anyway, so once you do it, if you have programmed it correctly, you will get about 90% accuracy. Okay. Or maybe even less, maybe 85% accuracy. So one of the plots I'd like you to do is, so number of hidden layer neurons. Okay, and accuracy. So for example, this may be, actually it will be, accuracy will be low, it should be the other way. So it will go something like this, right? Maybe this is 80%. If we increase, okay, then it will start to saturate basically, or maybe even get worse. So anyway, it will be something like this. So what is the good number of hidden layer neurons? Through experimentation, you will tell me what's that number, right? Okay, does high number of hidden layer neurons, is it always better? So high number of hidden layer neurons. Okay, so the question is it always better? And the answer is no. Okay. In fact, if we put too many neurons, okay, so too many hidden layer neurons, okay, makes the model too complex. Okay, and this results in what is called overfitting. So in the next lecture, we'll take a look at what are the techniques for avoiding the overfitting. So then you'll apply to this assignment and make it better. Okay, but very simply, very briefly today at least, suppose you were, forget neural networks for the time being. Okay, suppose you were given some data points. Okay, and you were asked to do like a third order approximation, meaning some polynomial ax cubed plus ax squared plus bx plus c. Okay, so you were C and D. Okay. So let's say you applied linear least squares, you came up with a third order polynomial, and it looks something like this. Okay, so you can see it did a pretty decent fit. Okay, let's pretend there are some outliers, meaning some noisy data. So there is some data over here, data over here, data over here, data here, data here. Okay. What if you did like a 7th order approximation to the same data? Then what you will see is it will try to do something like this. Because a 7th order can now have like 7 peaks as an example. So it will basically go through each one of them, okay, and do a perfect job. So you might say, oh, 7th order is a better answer to this problem. In reality, it's not, because the noisy data was causing the additional things. So if we go beyond a third order, it's really overfitting the data. So it's basically trying to accommodate every point it can. So same thing goes for neural networks. If we put 100 neurons, or let me ask you this, what if you created a single neuron network? What will it do?
Round effect.
What kind of,
Linear.
it will create a linear decision boundary, right? If I put a couple of neurons over here, I will do something like this. If I put 100 neurons over here, then now I will try to do something like more complicated. If the data is complicated, sure, it's fine. But if it's not, then it's overfitting the data. Let me see if I can show you one quick example. And then next time we'll go into the details of how do we prevent overfitting and what are the techniques. So there are some regularization techniques, there are dropout techniques, there are artificially enhancing the data technique to prevent overfitting. So we'll go into the details of those. But let me see if I can at least show you one example before we stop for today.
Professor, if we use all these 60,000 images, usually how long does it take for the program to run?
Depends on how good of a machine you have. On a laptop, if you are using, it might take like an hour or so to train it. But if you have a GPU and you use the one of the libraries with the GPU capability, then you can reduce it. But in the beginning, like I said, I want you to do it from very low level, direct NumPy, so that you see it, so it will be slower. The more advanced libraries like PyTorch and TensorFlow, they have the GPU built into those as an option, so they run pretty fast.
Since we're only taking 1,000, how do we make sure that the data is distributed? Like we don't pick all 7 or all 10?
When I created the data set, I gave them equal 100 zeros, 100 ones, 100 twos, so I distributed it evenly.
Will we be getting the code for this, an outline code at least?
Yeah, I'll try to give you the outline.
So we have to distribute the data also.
We know that you have to download it.
Just give me 1 second. If I'm unable to find it, I'll show it to you guys next time. Okay, so hopefully this will run. Okay, just 2 more minutes and I'll stop. Okay, so anyway, let's pretend we have 2-class problem. Some blue dots, some red dots, right? So if we pick a single neuron, right? A single neuron, as you can see, is a straight line type of. Okay, so this is, for example, if we train it, when we use a single neuron, we refer to it as a logistic regression. Okay, so you'll see it did 85% of the accuracy. I don't know if you can see some blue dots. So this is the decision boundary created. Okay, so anyway, now if I close the program, and I'll give you the okay, so suppose I use two hidden, so my, I'll give you the code later, you can play with it. So if I just put two hidden layer neurons, then how does the decision boundary become? So anyway, this is the single neuron. Then as I train the two-layer network, okay, so do you see the two-layer, it became a little bit nonlinear, a little bit better, but still not the best. 87% is the accuracy over here. Now, but if I go to 3 neurons in the hidden layer, okay, so the first one is again the logistic regression, which is basically a straight line boundary. So do you see it got a lot better now? Okay, and the accuracy became like 97.5 accuracy, so the few points. Okay, so the question was, what if we keep making the model more complex? Is it always better? Okay, so what if I make it, let's say instead of 3, 10 neurons in the hidden layer? Okay, so what will it look like? Okay, so even though it says 99% accuracy, okay, but what it's trying to do is it's trying to accommodate each and every point. So it's trying to memorize the data. So this is actually not a good result. So in reality, when we create the data set, that's why we have a complete separate test data. See, in this case, the test data is the same as the training data. So so we can't really, and if I make it 100, then you'll see it will become even stranger and stranger shape. So let me just make it 30 for right now to save time. Okay, so last thing, then I'll stop. Okay, so anyway, again, accuracy becomes 99, but maybe there should be a smooth curve right here rather than going inside and trying to accommodate the data. Okay, so next lecture we'll take a look at the overfitting issues. How do we decide what is the proper number of neurons in the hidden layer? So for that we